So hello everyone, I'm Anisha Mahinoor Ferdous. There's something very important today about very powerful software for your photovoltaic systems, which is PVsyst software. And our trainer is today engineer Saurav, who is working as R&D Officer in EEE Department of IUB, and he has completed BSc and MSc in Electrical Engineering. So I'd like to give the floor to Razak sir, who is our branch mentor, Dr. Mohammad Abdul Razak sir. Sir, say something for our students and our other fellow members as well.
Okay, thank you, Anisha. So I saw a lot of people, and hopefully, I don't know how many people registered.
100, 130.
130. Okay, from
Yes, sir.
how many universities? 15 or more? Yeah, I saw the name 15 probably. So I'd like to welcome all of you to this workshop. So this is the workshop actually organized by the IEEE Industry Application Society, IUB Student Branch Chapter. So today actually we have with us also the counselor, Dr. MD Kafiul Islam, the branch counselor of IEEE IB Student Branch. I am actually not only the mentor of this branch, but the founder counselor of this branch, serving as the advisor of IEEE Industry Application Society Student Branch Chapter. I saw Shoaib Shahriar, probably he joined from Saudi Arabia. So he was our colleague, and now he's actually in the teaching position as an assistant professor of Saudi Arabian University. So nice to see Shoaib Shahriar. I'd like to welcome you also. So students, guys, you can understand actually the importance of this workshop. You see that an assistant professor from a foreign university who was with us previously, who also joined with us. Okay, and me and also Dr. Kafiul Islam, we have actually another master's thesis defense will be starting from 7:30. So we will have to leave, and then again we will join. Actually, I will join. So let's talk about something about the workshop and the trainer. So this workshop is based on basically the photovoltaic system design, and we have actually many such software, but PVsyst, although this is a very old software, but this is simulation soft is very powerful. And about engineer Saurav Das is actually completed his BSc and also MSc in Tripoli from Independent University Bangladesh, but he has 6 month experience in Germany. So he is actually, his research area is this one. So he is working as a research and development officer of our department. Not only that, he is also with us in the Green Energy Research Center at IUB. So he is actually my research collaborator. So we have actually some publications, research publications together, and we are working also. So I thought that these workshops, the students will be joining from more than 15 universities in not only in Bangladesh but also from abroad. So the importance of this workshop is this is the first time actually we are going to conduct this kind of workshop we are organizing. And Saurav Das, hopefully in the next 2 hours or more probably, this depends on him as well as also with the participant, but would like to conclude the workshop by 9. So since we are 7:10, probably we are going to start, then maybe 10 minutes or depending on the trainer and the mutual understanding, maybe 30 more minutes we can go. With that, I would like to welcome all the participants who are joining from different universities from home and abroad. And I'd like to special thanks to our trainer today, Engineer Saurav Das, that he is going to take this kind of training for us. And always, actually, I learned almost all new thing from my student. So this is my 5 years of my teaching running this year, but still I'm learning from my students. So learning is actually from birth to death. So you can see that there is no age of this one. So hopefully you guys can take something from this one. But what I can say is that this is a getting started. So those who don't know about this PVsyst, for them this will be the getting started. So take this opportunity, and from here, and then just do practice and practice in future, so that you can continue with this kind of photovoltaic system modeling. So with that note, I'd like to thanks also the IEEE Industry Application Society IUB Student Branch Chapter, as well as the co-host of this workshop is IEEE IUB Student Branch. So I'd like to thanks all the volunteers to organize this kind of workshops. So hopefully this will be a very successful workshop. So for the next 2 hours. So thank you very much, Anisha. Over to you.
Thank you so much to our branch mentor, as well as we have our branch counselor, Dr. Kafil Islam sir, with us. Sir, do you want to say something to our trainer or our volunteers or participants?
Assalamu alaikum. Thank you, Anisha. Thank you, Professor Rajat sir. I think he has summarized the importance of the workshop, and he has introduced the trainer pretty well. So thank you, Rajat sir, and for initiating this workshop. I understand from the amount of registration happening, there is more than 100 registration, and from at least 10 different universities, what I have seen. So I'd also like to thank Dr. Shoaib Sharia from Saudi Arabia to attend this workshop. Thank you. Your presence will be very encouraging for our students as well. So I think over to you, Anisha. You can request the trainer to start. Thank you.
Thank you, sir. With that note, as I mentioned earlier, that this is a very powerful software, so we won't take much more time. I request our honorable trainer, Engineer Saurav Das, to start the workshop from now.
So, hello everyone, I am Saurav Das, and it's my immense pleasure to see all of you after, a long period of time. And, during this Corona pandemic, it's also so much boredom for me, because it was so much tough for me to make one-to-one discussion with all of you. So I'm really pleased again to see all of you, my students. Thank you for joining this session. So before going to the main topic, that means before going to the knowing how to use this kind of software, first I would like to introduce you some of the basic knowledge about this PV system. So let's start. So okay, so we are going to the background portion, and here, as you can see, this slide actually depicts the we know all of this, and renewable energy sources like solar photovoltaic system is there, wind turbine system is here, biogas and biomass, we already know, geothermal process is here, and also the hydroelectric power plant is in here. So renewable energy, what does it mean by renewable energy? So renewable energy means we are extracting or harnessing that kind of energy which from that kind of sources which can be reusable, or that can be renewable. So ultimate the concept is that, so renewable energy sources are that kind of energy sources which has abundance availability in our nature. So let's say for solar photovoltaic system, so how it works, we know that photovoltaic means, if we concentrate on the word photovoltaic, so photovoltaic means it actually, converts the photons into voltaic system. So that means it converts the solar energy into the electrical energy. And then if we consider about the wind turbine, so what does it mean, how it works? So whenever the air flows, it actually, the blades of the wind turbine, it cuts the airflow, and thus we are actually converting the airflow into the, electrical energy. And if we consider about the geothermal energy, so it's actually, extracts the heat, which actually, ultimately they are stored in our earth, and by using that heat energy, it's actually producing the renewable energy. And if we consider about the biogas system or biomass system, so what actually in which way it actually works, it works like produce methane gas from raw materials like agricultural waste, food waste, or plant materials, something like that. And then if we talk about the hydroelectric power system, so as you can know that we already know that whenever we make a barrier or dam, and then if we by using the, the concept of the physics, like the kinetic energy, we are actually whenever we are actually storing the water in a reservoir or in a dam, that time the potential energy stored in that dam, it actually converts into the kinetic energy. And this kinetic energy, by using this kind of kinetic energy, we are actually, rotates the turbine of the generator, and that's how we are actually getting the hydroelectric power. Now, one fundamental question is, among all of these renewable energy sources, if anyone asks you that which one is the, basic or fundamental energy source, so in that case I would say the solar system or the sun is the fundamental energy source. If the sun actually exists in our planet, then all the whole system will works properly. So now you may ask me that why, and why I am talking about this, and how I am saying about this, that sun is. So let me give me the chance to share with you like this drawing. So let's say I'm actually just think about it, that we are in a sea beach, just only for imagination I'm talking. Let's say if we consider about the sea beach, so let's say that here is the ocean, that means the water level in here. So whenever the sun shines, so that time the surface or the the sea, the sands around and the surrounding, which are in the sea beaches, they are actually get so much heated rather than the air which are surrounding in the ocean portion. Okay, so whenever the the air, they are actually getting so much warm, so that time the molecules of the air, that time they will get expand. Okay, so that means it will be not in a shape of low condensed. So how it will react, so that time this warm air, it will go in the upward direction, right? So it will go in the upward direction. So whenever it goes to the upward direction, so there will remain a certain gap over here. Okay, so since this place, there remains no air, so what happens at that time, since we are saying the air which is surrounding in the water portion, they are actually that they are actually that amount of air is actually not so much warm than this one. So it's actually, I would say, it's cool air. So cool air participant, and it is actually so much dense. The dense is so much higher. So what it actually do, it will fill these gaps. Okay, fill these gaps by the cool air. So in this way, actually, I would just only want to illustrate that the air actually circulating through the whole world. Okay, so if the sun is there, and then the air circulation will be in here. So if the sun is not in here, so the air circulation will not be possible. Okay, so whenever the air circulation is possible, that time we can use the wind turbine. Otherwise, not. So in that way, we can say, or we can come to the conclusion that If the sun is air, sun is or solar power is exist, so that time we can say the air power is also will exist. And then once again, if we say just consider about the hydroelectric power system, so in which way it works, it also works in the same way. Like whenever the water surface or the molecules of water, it also gets heated up. So what it happens, it actually vaporized, right? It actually vaporized and it actually goes to the upward direction. And what happens then, whenever it goes to the very high altitude, so that time it gets so much dense, and after some days or after some portion, whenever it goes, whenever it comes to these solar areas or sunny areas, or in the rainy seasons, so that time what happens, it actually makes the clouds and it actually starts to rain. So whenever it rains, so what happens, so all the ponds, all the ponds and all of the watery, watery places, it you know gets flooded. Okay, so if we consider about a fountain system, so that times what happens, a huge amount of water comes, and if you make a barrier or if you put a dam over it, so that time it will act as the it will definitely access the hydroelectric system. So thus we can say the hydroelectric system also depends on solar energy. And then if you just consider about the what's up about like just let's consider about non-renewable energy sources. So let's talk about like wood or something like that. We actually burn it out. So whenever you burn it out, so what kind of energy it is actually releases, that is also part of it, the solar energy. So I would say if the solar power or the sun actually exists in our earth, so that time each and every thing or each and every other and renewable energy sources will be exit. So thus we can say that renewable energy sources is abundance in nature. So let's come to the photovoltaic systems, like types of photovoltaic system. One is like on-grid system or grid-tie system is there, and another is off-grid or standalone system. So let's come to the point, on-grid system or grid-tie system. So actually on-grid system or grid-tie system is applicable for urban areas or rural areas. It doesn't matter. The matter is the household system must have to be connected with the national grid. So here, as you can see, the house is connected with the national grid, and the energy actually goes to the energy meter, and it is via the junction box is actually connected with the AC appliances. And here the solar panels are here, and it's connected. It also produces power via the inverter, and via the net metering system, it actually can give the or feed the excess power to the national grid. So let's come to the point that there remains some advantages of this grid metering system or grid tie system. The main advantage is there remains no battery backup system is required. No battery backup system is required. Why? The excess amount of energy which you are producing, you can feed it to the national grid via the net metering system. And the net metering system is also introduced in our country, so it's a plus point. So I am showing you the just only the single line diagram that how it works, like 11 kV line by using the transformer 400 volt line. And as you can see, whenever it goes to the consumer load, it actually goes via the energy meter, and which is net metering system, and it is bi-directional. So bi-directional means that means in both direction, in it can supply or it can gain the energy. And here, as you can see, the PV panels, they are also connected via the grid tie inverter, and they are also connected to the main distribution board. So here also some optional meters in here, like energy meter is in here, and another renewable energy meter is in here. So the thing is that they will just only calculate that how much of how much of energy is actually being produced by the renewable energy sources, and it will consider that how much amount of energy you are getting or you are using. And this bidirectional meter will actually calculate or will keep the track that how much amount of energy you are feeding to the national grid. Now I just only want to show you that uh, as we know, since it's so much important and crucial, so that's why I'm showing it to you, that we are actually getting power or getting the energy from like DPDC, DESCO, BREB, PPDB, something like that. And these organizations will buy the energy from you. However, the main point is that let's say you are buying the energy, that means per unit at 5 taka. Let's just assume whenever you want to sell to these distribution companies, they will not buy the same amount of energy at the same rate. Okay, so whatever they will do, they actually buy the energy from BPDB. Okay, so let's say they buy the same amount of energy from BPDB at 3 taka per unit. So whenever they are buying the same amount of energy from you, they will give you 3 taka, not 5 taka. Okay, and then come to the off-grid or standalone system. So standalone home system is that kind of system where there remains no national grid. So that means national grid is totally absolute in here, no connection. So here, as you can see, there remains a solar panel in here, and it is directly goes to the charge controller, and the outcome of the charge controller, it goes to the battery, and the outcome of the battery, it goes to the inverter. And what inverter does, it converts the DC power into AC, and that's how the AC appliances works. So actually the charge controller, what is the charge controller? Charge controller is just only the buck boost converter, nothing else. So what actually do, whenever let's say the input voltage of the of it is 12 volt and your battery is also 12 volt, so it actually slightly increase it, let's say 14 volts, so that it will charge. Okay, so the battery section will get charged. And whenever let's say the input voltage is lower than that, let's say 8 volts, so that time the boost converter mode will be activated. So that time it will increase the value, let's say 14 volt or 13.5 ampere, so 5 volt. So the main portion of the charge control is just only to the buck boost converter system. That's it. So there remains also some positive side and negative side of grid system. Positive side is no requirement national grid. However, and the cost is cheaper. However, the negative side is that backup system is required. That means battery backup system is required, and sometimes to make sure the 24 hours of 4 hours of electricity connection, sometimes backup generator system is also required. And here, as you can see, solar cell array and string. So whenever you are connecting the cells in series, so that time we say module, and whenever the modules are in series, we call it string, and whenever strings are connected in this, we say it array. And it works exactly same as the battery system. So let's say one solar module is 6 volts. So whenever we are connecting it in series, so that time it will act as like 6 multiplied with 3, it will be 18 volt, but the current remains the same, so 3 ampere. Whenever you will connect it as the parallel system, so that time it will be like 6 volt. However, the current will be 9 ampere. So that means the main or total power, it will be remains the same. Now comes to the main point. So we are right now narrow down our topic into the photovoltaic system design. So whenever you are trying to do the photovoltaic system design, so that time you have to think, or you have to consider all of this situation, like what will be the distance from one solar panel to another solar panels. So the distance between the two solar panels will be the d, and the distance d is equivalent to 3 multiplied with w. So w means the width of one solar panel. And now let's come to the tilt angle. Here, as you can see the world map, where it is specified in which region we have to consider which value. So let's say we are in here. Of course, we are in Bangladesh. We are surrounded by the India in 3 directions. And its color is like this, and it colors states that the solar tilt angle, it must have to be 13 to 26 degree. However, in our country, maybe it sometimes is 23 to 29 or 30 degree. It's okay, it's fine. And we will analyze it in software, that which will be the best tilt angle for our for our place, or for our esteemed or desired place. Okay. And then as you can see, whenever you are going to do the calculation by mathematical analysis, so that time you have to consider the real photovoltaic modules data sheet. So what we actually need, it actually shows you the standard test condition, STC. So STC is actually defines that whenever it is like 25 degrees Celsius and the solar irradiance will be 1000 watt per meter square. And the ISC is short circuit current, it is also important. So here, as you can see, it is 7.45 ampere, and the open circuit voltage is also important, it is 21.5 volt. And if you operate this solar system in maximum power point tracking system, so that time the VP maximum voltage, it will be like 16.9 volt, and the current will be 7.10 ampere. Let's come to the point equivalent sun hour. Okay, so sometimes you will know it as like you will find it like peak sun hour. So what does it mean? It if we consider in here, so like in Bangladesh, since we are in this region, it is yellow, and here as you can see the value is 4.6. What does it mean? 4.6 kilowatt hour per meter square. So what does it mean? So it means that 1 kilowatt amount of power you will get for 4.6 hours. Okay, so sometimes in somewhere you will get the value as 4.6 kilowatt hour per meter square, or somewhere you will find the value as 4.6 hour per day. Okay, and then come to the next topic. Yeah, right now we are going to photovoltaic system design. Okay, so let's consider one case, and that is actually, first of all, I want to go through the grid tie system designing steps. Okay, so what I will do, or what we will do, so first we have to consider that how much amount of energy is actually required, okay, from solar power. So here, as you can see, here remains a chart which shows the yearly electric uses, and here the 12 months in here, so that means for whole year round. And the unit, especially in the electric bill, you will see that it's written is unit, not kilowatt hour, but as we are in electrical engineering, we know that it's actually a kilowatt hour. So here, as you can see, January is 1606 unit, February is 1212. So let's come to this step by step. Okay, so first of all, what we have to do, we have to determine the annual daily average. So how to do it? So at first we have to sum all of these units, okay, in kilowatt hour, and then divide it by 365. Why 365? Because we know 365 days in a year. So thus we can get 50, like for here, just only for an example, it is 50 kilowatt hour per day, okay, for this case. And then we have to know that how amount of kilowatt is required from PV system. So we have to, what we have to do, we have to divide this kilowatt hour per day divided by equivalent sun hour, which is unit is hour per day. So here is 4.6. So we are getting 11 kilowatt. So after considering the system efficiency of 77%, so what does it mean? So we are considering the whole system's efficiency will be 77%. Okay, so that means a lots of losses in here. So we are considering the loss will occur in wires, DC to AC conversion loss, and diode loss, inverter loss, connection loss, a lots of. So if we consider it, that time the 11 kilowatt divided by 77% give us 14 kilowatt system. So now we are in a position that we have to think, okay, so the total amount of energy which actually is required for us per day is 14 kilowatt. And now it's my choice. I will get the 100% of it from solar, or I will get some portion of it. So for this case, let's consider that we are choosing 50% of this. Okay, so 50% of our requirement will comes from the solar energy. So our required power is 7 kilowatt. Okay, so now we have to consider some grid tie inverter specification and also the PV panels specification. So for this example, we are just assuming the for grid tie inverter system, the power is 8 kilowatt and the input DC voltage range is 300 to 480 volt. And PV panel specification, let's say one PV panel is 300 watt, open circuit voltage is 27 volt, and 11.1 ampere. And we are actually considering the system voltage will be 360 volt. So you may ask me the question, why actually I choose 360 volt? Why not 300 or why not 480? So it's not a big deal. Okay, so we are actually avoiding the lower value and also avoiding the highest value. Okay, so we are actually choose a medium value, and we choose is 360 volt. It's okay, it's fine, no matter. And then so we are actually calculating that approximately how much amount of solar panels required. So 7 kilowatt system, we are dividing it by 300 watts is our one solar panel is actually 300 watt system. We consider that one PV solar panel is 300 watt. So whenever we divide it, we got it like approximate result that 24 panels is required. So now comes to the point that okay fine. Okay. Now we are trying to calculate that how much amount of solar panels will be in series connection and how much solar panel will be connected in parallel connection. So let's say series connection. So what we have to do, we have to divide the system voltage by the open circuit voltage of PV panel, and we are getting it like 13 panels, 13.333. So we are not considering the fractions, so it would be like 13 panels will be connected in series. Now parallel condition. So number of parallel connection will be solar panels considered. We have considered the rough value. It was 24 panels. 24 divided by what we got 13. So divided by it is actually 1.84. So approximately 2 panels in parallel connection. So the total number of panels which is actually required 26 panels. So now calculating the powers from it, so 26 panels, and as far as I considered that okay, each PV panel specification is one PV panel, it will give us the power 300 watt. So 26 panels multiplied with 300 watt, it is like 7.8 kilowatt, and which is under the coverage of our inverter specification because we choose the inverter as 8 kilowatt. So, and here the grid inverter design system, just reading materials. If you want to know a bit more about it, how to make the inverter design, you can download this paper from ResearchGate and read. And now let's come to the point. We are going to play with PVsyst software. So all we are ready.
Yes, sir, you can start.
Okay, thank you. So here, as you can see, here is the version is 6.70. So it doesn't make a big deal. You will get the latest design from the download link, and they will give you 30 days full free license you will get for 30 days. So it's okay. So it looks the same no matter what it is. So let's come to these sections. So what are we are going to do? We are going to design a on-grid system or grid inverter system. So here, as you can see, there remains some options like preliminary design, project design, databases, and tool option. So first of all, what we have to do? First, we have to go to the database option. So why we will go to the database option? Because we have to include the geographical attributes to this system. Okay, we have to feed all of the geographical information of our selected place, and we have to include we have to feed all of this information in this software. So first we have to go to this Meteor database geographical sites. Okay, so let's consider it. So now you may search over it here, but it's actually not generally I would say it's actually not included. Let's say if you go for the Gazipur district or Gazipur and or any other Borishal, and there the longitude and latitude will not be in here. So what we have to do, we have to go to the new section, right? Okay, and then we have to go to the graphical coordinates. Okay, so first site name. So we have to make one references, right? Reference site. So what it will be, I just consider IUB, that means Independent University of Bangladesh, as our reference site. So I need the name of it. I am naming it IUB. Bangladesh. Okay. Site name, country is Bangladesh. Sorry. I've chosen, and the region is Asia. It's fine. So now comes to the point, what will be the latitude and longitude, altitude and time zone. So some information I already know, like in Dhaka, we know the time zone is +6. Okay, and then we need to know the latitude and longitude of IUP. So let's come how to do that. So we have to go to Google, Google Map. Okay, so let's try to do it again from first. So Google Maps in here, and then we are going to search like IUP. So it's already written here. So it okay, it appears that okay, in this portion IUP is located. So now then what will you do? You will choose the what's here option. So if you choose what's here option, that time you will get the latitude and longitude in here. So what we have to do, we just try to, sorry, okay, what's here, longitude, latitude. Okay, so if we click in the same thing, so that time you can see here the latitude and the longitude value is already showing. Okay, so what we'll do, we'll just copy and paste this value. So first copy the latitude value, and then we are just copy paste in here latitude, and then copy the value of the longitude and paste it in here. Now let's come to the portion altitude, and it's showing the unit, it must have been meter above the sea level. So just go through the Google and you will see the altitude of Dhaka city is 4 meter. So just we have to do, just type in here 4. That's it. So our is already done. And then meteor data, we have to input the meteor data. So here there remains two options. One is meteornom and another one is NASA. However, I prefer actually the NASA because it's all known institution. It would be great if use the NITA. Sorry, NASA. And then what we have to go do, we have to import it. Okay, and it actually showing. Okay, that okay. So it will use the database like 1983 to 2005 data. So let's okay, and it's the satellite data is actually collecting the information for this latitude and longitude. Okay, and then here we are getting the all of these values. So just click like kilowatt hour per meter square per day. Here as you can see the global irradiance is a kilowatt hour per meter square per day. Yearly is on average is 4.65, which I actually showed it to you. The equivalent sun hour is 4.65 for Bangladesh region. Okay, so what we have to do, we have to go for just okay. Okay, and it's calling that okay, is it okay, just save it, and it's just okay. Yeah, it's showing that IUP Dhaka Bangladesh, the NASA data is already included. Okay, so close. Fine. Now come to project design. So we are going to first of all we we will go for grid connected system or grid tie system. So let's choose it. Okay. So what we have to do, we have to go for first of all we have to choose like new project, and then just write it down the project name. Let's say I'm choosing anything you can just give it a name. I think IUP. Okay, project names, a new project. Okay, it's okay. Site 4. So let's choose the site. Open a site. Please load the geographical data. Okay. Okay, so we are loading the geographical data, and which is IUP Dhaka, Bangladesh. Okay, and it's also actually show it that okay, right now you have to save the project. Okay, so I am right now going to save this project. Okay, new project, fine, save it. Now it tells you what you have to go. You have to choose the orientation, and then you have to give the values for the system. So let's go for the orientation. Okay, fine. So here, as you can see, the tilt angle and the azimuth angle is showing. So what is this? We already learned it. The tilt angle for Bangladesh or in this subcontinent, it would be like 13 to 26 or 29 to 30. It's okay. So how to calculate it, or how to get the ultimate power or ultimate result, that okay, in this tilt angle and in this azimuth angle it would be defined. So we here there remains a lots of options, but for the simplicity we are choosing fixed tilt plane. Okay, and we are choosing the optimization, it would be for yearly irradiation yield. Okay, not for summer, for winter. But if you consider for focus on summer, so you can choose summer. If you focus on winter, so you can choose winter. But I am actually choosing for yearly irradiance yield. Okay, so now if you choose like this, show optimization, you will see a map. Fine. So let's assume that our tilt angle is, let's say, here as you can see, whenever it is 30° and the azimuth is 0°, that time see the loss is about 0.0%. That means there remains no loss, and it will give you the maximum amount of power, 1.2 kilowatt. However, if you just change this value, let's say I choose it like 29. If I choose the tilt angle as 29, look, it is also the same. Okay, no problem in here. Let's say choose like 15. Okay, the tilt angle will be like 15 degrees. So look, the power it actually getting decreased. It is not in the peak position. Okay, and it shows that okay, there remains some losses, and we will get minus 2.8%, 2.8% losses. Okay, and if you consider it would be like perpendicular, so if you choose 90°, let's say choose that time it will get a huge amount of losses. It's like this point is here like 0.68. So it's so disaster system. Okay, so someone says it to me, especially I have heard it from my students and some other colleagues that say that some other countries it actually they choose the tilt angle as 0. So that means it will be flat. The solar panel it will be flat, and that means it is horizontal to the ground. And they said it's the best decision they have ever made. But what we are seeing in here, the software actually shows it to me that there remains a huge amount of loss. However, whenever you are going for the economical analysis, that time you will find it out okay, there remains a lots of cost issues. You will give it, this will make your system feasible. Why? Because whenever you are considering a tilt angle, there remains a lots of infrastructure issues, lots of costs are there. So thus they are actually minimizing the cost. However, we have to keep in mind that for energy harness issue, it will get lower amount of. Okay, so as far as we get, okay, so after all of this analysis we got the perfect, it would be 29 degrees of 29° tilt angle for our specific area. Now comes to this point, azimuth. What is showing, what does it mean? Look, if we consider it as a solar panel, and here as you can see it is perpendicular to the south direction. Okay, and if you consider azimuth angle, let's say 15°. Yes, I'm consider azimuth angle as 15°. So see
সৌরভ
the
সৌরভ সৌরভ
sir, yes sir.
ওই তোমার স্পিকারটা এই মাউথ থেকে একটু দূরে রাখো।
Okay, sir. Now it's okay, sir. Okay, so whenever the azimuth angle is 15°, it actually makes 15°, to the west. Okay, if we consider the west direction is as the main point or main axis, so that time it will create 15°. Yeah, we refer to the west direction. let's say if we consider 45 degrees, so it will make 45-degree angle with the west direction. If we consider it 90, it is totally perpendicular to the west direction. So it actually rotates. So however, as you can see, whenever we are actually rotating it, so the power actually goes to decrease. It decreasing, power decreasing. We are not harnessing the optimum value, optimum amount of energy. So we have seen it like whenever we choose 0 degree, so that means it's in the parallel with the ground, the west direction, and that time, and it facing to the south. So that time we will get the maximum amount of power. So we are choosing this orientation. Now comes to the system. Okay. So whenever we are coming to the system, that time our mathematical analysis, which we have already done, it will help us. Okay, so it will help us a lot. So let's come to that portion. What we have considered for grid tie system. Okay, so here is the calculation. Okay. For grid tie system, we have calculated that our requirement was like 7 kilowatt, right? 7.14111478. Okay. So let's choose this. What we have to do, we have to go for enter plant power, and what we choose like 7.7.14 or something. 1478. Just write it down. 7.2 actually. 7.1. And it's showing that okay, our tilt angle is 29, azimuth is 0. Now we have to choose the PV module. So here there remains a lots of option available now or production from 2003, 4, 6. It's just like the Proteus software. There remains a lots of solar panels, stimulated design, and all of these criteria, all of the data sheet you will find it here. So it's really nice. Even you can choose a lots of solar panel making industries like ABB, Generic, AEG, lots, Voltaic Cleaner, HPL Power System, LUC, no matter what. So here you can see as you wish. So I am choosing like okay, so I'm choosing available now. Okay, no matter what. So just I'm actually considered is 300 watt power, 28 volt. As far as I can remember, we considered 300 watt system, right? Yeah, 300 watt system for solar panel. So I am actually considering. And now let's come to the portion inverter section. What kind of inverter we're going to use? So available now, okay, fine. And there, we can choose a huge amount of companies, ABB, Aerosharp, a lots of huge amount of, you can just choose, just play with it. Okay, so no matter what, Delta Energy is so nice for any students, any scholars, so nice to play, just play. So you can choose any one of it, but I prefer to choose the ABB since it's so much operative company, so renowned company, transformer section, inverter, as you wish, you can choose it. And I would prefer, and I just give you the suggestion, before going to choose any kind of models, just go through the market analysis. Okay, maybe in Bangladesh here, what we are actually choosing the solar panel, maybe it's not in the market, the same company. So what do you have to do? You have to just go for the specification, the same specification, like uh, 300 watt power and the 28 volt. It would be like PMPP, and maximum power point voltage. It would be like 28 volt, and open circuit voltage it would be like 44.9 or 45 volt. You have to just only go through the specification, do the market analysis in local areas, and then choose the right one. Okay, so let's come to the point ABB. Okay, so there remains a lots of inverter sections in there. So since our plant is 7.1 kilowatt, so we have to choose like 7.1, exactly 7 or little bit more about it. Okay, so here just I want to give you one crucial information, that whenever you are going to design the on-grid system, let them try to make it similar. Let's say if it is 7 watt kilowatt system, let them try to choose the inverter 7 kilowatt. If it is like 8 kilowatt, let them choose 8 kilowatt inverter section. Okay, so right now since it is 7.1, so I have to choose 7.5. Okay, so here as you can see 7.5 kilowatt is in here. The input DC volt, it can varies like 175 to 950, so it's good. Okay, 50 hertz system, so that means the outcome it would be 50 hertz, and is the model number, and the since 2013 is in under production. So let's choose it now. It actually give us some issues. Look, here it is actually showing us some notification. What it says, we should read it. So it actually says that you should define at least one string per inverter or MPPT unit. Okay, so that means MPPT. Look, here is actually use the multi MPPT feature. It actually okay, two strings, two input. It actually says that okay, you have to maintain this one. Look, automatically the software actually give us a suggestion that for this system, what we actually choose for solar module, it actually automatically calculates that in series connection there remains 24 modules, and the parallel string it would be 1. Okay, so now you can choose. Now you can make it okay. You can play with it. Here it is showing it that between 7 to 20. And here it's also important that it says that if there remains, let's say, two string. So here is the problem is we are actually choosing one string, but the MPPT is for two inputs. So what we can do, we can make it two. So parallel it would be two, and this would be no problem. I would say no issues here. Why? So now it's okay. So how it okay? Because ultimately we require 24 number of solar panel. So what we do, we are actually choosing the 12 solar modules will be connected in series and 2 will be in parallel. Okay, that means parallel string it will be 2 and 12 solar modules it will be connected in series. So that means total 12 multiplied with 24 we are using, and since this string is 2 and we are using for 2 strings, that means for both strings that can be. Now it's okay, and what it shows, like another notification, the inverter power is slightly oversized. Okay, so why slightly oversized? Because our required system was like 7.1 kilowatt. However, our inverter is can handle little bit more, like 7.5 kilowatt. For that reason, it's but it's not a big deal. It's really nice. But fine. Now come to this point. Really, operating condition is actually showing and projecting that the maximum power point, that means at 60 degrees Celsius, the voltage of the solar panel, that means these solar panels, the formation of the solar module system, it will be 337 volt. At 20 degrees Celsius, the voltage will be 405 volt. At open circuit voltage, now come to the point. Look, here there remains one pattern. Whenever it's 60 degrees Celsius, the output voltage will be 337. Whenever it's 20 degrees Celsius, the voltage will be 405 volts. So what we have learned? We have learned that whenever the temperature decreases, the outcome of voltage of the solar module will get increases. So it's also one basic information all have to know. And whenever we are going to design it by manual, we have to consider it in mind. And VOC, look, open circuit voltage, it's minus 10 degrees Celsius. As far as I know, we are in, if we consider we are in Bangladesh, so there remains no chances that the temperature will go beyond this level. However, we have to consider this because there remains a proverb that stay in local but think global. So we have to think global for each and every country. Okay, so whenever it's 10 degrees Celsius, minus 10 degrees, the outcome voltage will be 530. Now match with this. Like whenever the solar panel outcome voltage is 530, does my chosen inverter will operate in this value? Yeah, it will easily operate in this value because the highest amount of is 950. The plain irradiance, it is also showing the current. Okay, so at STC, the IEC, what it will be, standard temperature condition. So that's it. So maximum amount of power 6.5 kilowatt, array nominal power 7.2 kilowatt power. So exactly okay. So no issues over here. So just go okay. The inverter power is slightly oversized. Warning is okay. No problem. Now comes to detail losses. So actually, if you go to this section, you have to give a lots of losses in here. Since we are in fundamental level, so I would recommend you not to deal with this right now. It's not so much required right now. So we are actually choosing the standard values of it. It's okay. Don't need it right now. Optional, you may give some optional information in here, like horizon values, near shadings. Whenever you the near shading, so that time you have to actually draw. Lots of drawing system is required. Uh, Keep the 3D analysis where the shadow can make a lots of effect, but right now it's not required. It's fundamental. It would be so much fine. And then come to run simulation. Fine, it's working. It's already done. Okay, simulation ended successfully. Then okay, new simulation you want to save? Yes, save, yes, and it's done. Now what we will do, we'll go to the report section. Okay, look, here the PDF file is already generated for our esteemed institution, loving institution IUB. We already chose it, the country Bangladesh, longitude, latitude is in here, all of this information is in here, the simulation parameters is already given, the chosen field angle, azimuth is there, the solar name, all of these issues here, know about it. Okay, so then here's next page. It connect your system, so it is important. Look, here it actually calculated the main simulation result. The produced energy is 11.57 megawatt hour per year. The specific period per year that shows 16.8 kilowatt hour per kilowatt hour peak per year, and the performance ratio is 82.24%. Now you may ask me the question, what does it mean by performance ratio? So performance ratio means, let's say if you choose all of this system in the standard condition, that means there remains no losses in the whole system. So it will compare the standard system with this system, what you have designed, and then make the value, make the ratio of it. Our ratio is 82.24%. That's pretty good enough. Good enough that our system is 82%. I would say no risk. And there, as you can see here, the graph analysis in here. So I want to zoom it. So here, as you can see, this red portion, it actually depicts you that the inverter useful output, which is 4.4 kilowatt hour per kilowatt hour peak per day, and LS it means the inverter loss, and LC is the collection loss. It's actually showing by this that okay, this one is the collection loss. Is LC is blue, so is the collection loss, and LS is the inverter loss. As you can see, the inverter loss is also there. So it's okay, it's negligible. However, the collection loss, PV array loss is huge. Okay, so huge portion. And performance ratio, the maximum performance ratio can be 1, that means 100% efficient. Can't be possible in real world. So okay, it's fine, 82%. So we are happy with it. And there's some other issues. It shows okay, it is the global hour. You already seen it from the NASA data. Okay, fine. So then go to the third page. Okay, very good. Right now we are going. We have come to this point, loss diagram, which is also very much crucial. So whenever you are loss diagram, whenever you are presenting the loss diagram to any conferences or any others, he or she can easily imagine that what are the main losses. So right now you can easily see that minus 11% loss. So is the largest loss. Okay. So minus 11% loss, it will loss due to the PV loss due to temperature. So whenever you are designing, you have the idea the temperature loss it would be so much huge amount. Then a loss of loss like 3.5% inverter loss there is a lot. Okay, but all of these other 0.0%. Inverter loss during operation, that is efficiency issue is also the loss. Even whenever the module is actually working on MPPT system, that time there remains also some loss. Mismatch loss is there. So it's so nice. Efficiency at STC, standard temperature condition. You may ask me the question, what is this? It's actually PV conversion loss. PV conversion, sorry, efficiency is 18%. So in the renewable energy field, so those who want to, enrich your, your profession or your research skill in renewable energy field, I would request you just only, there remains a huge amount of field to do with this, because till right now our PV, that means conversion issues in is really not so good enough. It's just only 18%. 18 to, as far as I know, is like 20%, not so much. Okay, so that means 80% of the total energy is wasted. So you may go through this, and we have a lots of options to increase our potential in this field, working PV issues. So it's fine. And energy injected into the grid 11.57 megawatt hour, and always remember it is per year value. Okay, yeah, and it's already showing it. Total nominal total is 7.2 kilowatt. It was required, and we have designed it for 7. Okay, so that's the question we have already done for grid tie inverter system. And right now we will deal with the off-grid system design. So let's go. Off-grid system design. So let's come to this point where right now we are going to learn about how the standalone system or off-grid system we can design. So here is the design steps, that what we have to do. We have to do the load demand, and then we have to calculate the days of autonomy. So days of autonomy means since there remains no grid system, grid tie system is not there, there's no grid system absent in those areas, hilly areas or rural areas. So we have to consider.
Sir, your audio is not clear, sir.
Okay, right now it's clear.
Yes, sir. Right.
Okay, so days of autonomy we have to choose like whenever, since we are considering the standalone system or off-grid system in those areas where there remains no grid. So as you know, the another disadvantages of the solar system is whenever it's cloudy areas or rainy times, that time we will not get enough solar power to convert in solar photovoltaic energy. So that time we have to rely on battery bank system. So days of autonomy is actually works for this reason. So we have to choose like for 2 days or for 3 days or for 7 days. We will be fine without any kind of sun. It's the weather issues actually, or backup portion. And then we have to we know the equivalent sun hours, and then we will calculate for PVR design. All of this information is required. We'll consider the accounting loss. Then we will charge control design our charge controller, battery design, inverter design, panel design. These are the steps. So let's explain. So here we are load calculation. We are considering the load calculation program. So here we have two options, that either you can choose DC, and you also can use the AC appliances. So AC appliances, when we can use AC appliances, when you use off-grid inverter. However, in this software, PVsyst software, there remains one disadvantage, that you can't design DC to AC systems for standalone system. Once again, I repeat, for standalone or off-grid system designing in PVsyst software, you can't make any kind of design from DC to AC system. It would be DC to DC system, but just only showing you, just only to let you know that in normal field or in practical field, you have the option to use DC to DC system, both DC to AC system, by using just only an off-grid inverter. But in PVsyst software, it does not allow you to use the off-grid inverter. That's it. But for manual calculation, I am showing it. So let's consider that our DC load is just light, 4 quantity, and per watt is 25, and the total power will be 100. And total time of use is 3 hours per day. So total energy is 300 watt. Now let's come to the point. We will use the TV and also desktop computer. So TV one quantity, and the power per item is we are considering 100 watt AC. Total power 100. Time of use per day 2 hours per day. Total energy 200. Desktop is also the same, 1 hour per day. 100. So total is 300. Now let's come to the point. Here we choose 2 days of autonomy. That means if there remains no solar power available, or if it is cloudy, or it is rainy season, 2 days at least I will get the full amount of energy. Let's come to the accounting losses section. Okay. So here, as you can see, the DC load, it will be directly goes to the charge controller and battery bank system. No inverter system will be in there since it's DC to DC conversion system. So it will go through this, and we are actually considering the charge controller, the efficiency of charge controller and battery bank. The total efficiency is 85%. And single standalone inverter, we are considering it has the efficiency of 90%. So 300 watt of AC. That means we have to do back calculation. So 300 watt of power of AC, and if it is gone through the inverter, so there will be lots of losses. So 90% efficient, so 10% loss. So we have to consider about it. So 300 divided by 90%. And then all of these will go through the charge controller and battery bank, so it is 85% efficient. So for this area, that means for photovoltaic array, what we will calculate, the 300 watt hour for DC plus 300 watt hour divided by 90% is for AC load, and all of this system will go through the charge controller and battery bank, so it divided by 85%. And the total amount of power which is required, we calculated is as 745 watt hour per day. Let's come to the equivalent sun hour section, or peak sun hour. As we have said, for Bangladesh it was like 4.6. So it actually from the another PowerPoint slide. It's from TU Delft. So the reference. So they actually considered it 4.5 hour per day. So no matter what, 4.5, 4.6, that's the point. So we are actually considering 4.5. So let's consider about the PV array. The PV array here, just chosen model is module like 100 watt power, MPP 16 volt, IMP 5 ampere, open circuit voltage 20 volt, and short circuit current is considered. It's just only in the reference that we are choosing this solar. Now let's come to the design. That how much or how many solar panels required by us. So minimum watt power which is required, we have already calculated that our requirement is 745 watt hour per day. So what we did, total energy demand divided by the equivalent sun hours, we got 165.6 watt is actually our minimum watt power. And then number of panels which is required, 165.6 watt divided by 100 watt power. So where comes it from 100 watt? Because each PV panel is actually 100 watt hour. So whenever we divided it, it was like a 1.7. So just we make it simple, it is going to be like 2 panels. 2 panels is required. Now comes to the configuration. Either you will choose the parallel connection or series connection. So if you choose that 2 solar panels, it will be connected in parallel connection. So that time the current issue is there. So maximum current Imax will be short circuit current. We have to 7 ampere multiplied with 2, it is 14 ampere. And whenever you want to connect all of the solar panels in series connection, so that time choose the voltage. It is 20 volt multiplied with 2, it will be 40. So now comes the charge controller configuration. So here just only choose. Okay, this is the MPPT charge controller. And it's actually written in the specification or in the data sheet. The maximum voltage which it can handle is 60 volt. Maximum amount of current which it can handle is 10 ampere. Operational voltage is 12 volt or 24 volt. That means it can operate in both of these voltage, 12 volt or 24 volt, no worries. And the MPPT option is available. So now we have to consider the PV panel with this system. We have to compare it. Like, let's go to the former slide. It shows that whenever we are connecting it in parallel, that time 14 ampere is required. So does it allow 14 ampere? No. The maximum amount of current which it can handle is 10 ampere. So that means this option we can't do it. Okay, we can't use that option. Okay. And then if we choose the series connection, then the operational voltage it will be 40. Now we can see, yeah, down because maximum voltage which it can hold, that is we hold, it is 60 volts. So it's in the range. So that means we are come to the final decision that solar panels we have choose it will be connected to these. Now let's come to this point, battery specification. We are actually choosing depth of discharge here is actually 60%. However, just only one information. In practical field, we are actually not choosing depth of discharge as 60%. We choose it 80%. Okay, not 60%. And if you make one graph, okay, so let's say in x-axis it is life, it is depth of discharge, and in y-axis if it is like life cycle. So that time I would say that if you increase the depths of discharge, and that time the life cycle will decrease. And reversely, if you decrease the value of depth of discharge, the life cycle will increase. So, however, there remains one cost issue also. Okay, so if you choose like 10% of the depth of discharge, so that means the life cycle would be so much higher. However, the from initial cost will be so much higher because you have to buy lots of batteries. But whenever you are choosing 80% or 90%, that time depth of discharge, so that means the life cycle cost or life cycle would be reduced. However, the main problem is since it is 90% depth of discharge, that means 90% amount of energy will be cut out from the battery. So that means the maybe the longevity will be get affected. So that means let's say 1 year or 1.5 year later on, you have invest a lot of money on battery. So it's really a crucial point. So practically we choose actually 80%. Battery voltage is here 12 volt. Battery capacity ampere hour is 21 ampere hour, and battery model is who. So now comes to the battery specification design. So minimum capacity of battery which we require. Total energy demand we already calculated is 745 watt hour is required divided by 60% depth of discharge and multiplied with 24 volt is actually the operational voltage which we choose. Operational voltage means the battery will be connected to the we have choose the solar module is connected to the charge controller, that is the 24 volt. So and the charge controller will also will connect with the battery. So here since we choose 24 volt as the operational voltage, here we also for battery section we are choosing 24 volt and then multiplied with days of autonomy. So as you can see, if you choose days of autonomy like not 2 days, like 20 days, so that time the total ampere hour will be hugely, it will impact, it will be huge. So that time lots of battery will require. And if you choose like 1 day, so that time this value will be lower, so you lower amount of batteries. So number of batteries in series, as you know, the in specification, it actually shows that the battery voltage is 12 volt. So 24 volt, yeah, you can easily imagine the two batteries, it must have to be connected in series. The number of batteries in parallel, so the ampere hour divided by 21 ampere hour, and it shows that 5 batteries is required. So number of batteries, 2 batteries will be connected in series because we have choose like 24 volt system, and parallelly it will be 5 strings, so it will be total 10 batteries is required. So fine, and let's come to this section, inverter specification. As I have already said it in PV system, PVsyst software, it will not give us this option, but in practical. So here, as you can see, the efficiency for this model is actually 90%. Operational voltage is 24 volt. So that time what we have to do, total power demand 200 watt. It was actually not 200 watt, it was like 200 watt. The total power demand, we already calculated it. Yeah, it actually we calculated it as 165.6 watt. But since there remains inverter, so we are actually we are actually not considering a fractional value. So we are considering what divided by the inverter efficiency 90%, which would be like 222. Okay, and if you want to learn about the off-grid inverter system designing, so you may download this research paper from ResearchGate. Okay, so it's already uploaded, and then now we will play with PVsyst software. So let's come to PVsyst once again. So I have to zoom it, right? Okay. So now we will make another project. Okay. So what we have to go? We have to do new project. So we are IUB of it. Then now we have to choose like site file. Okay. I have already choose the off-grid system. No, right? No. Yeah. I first have to go from this side. Sorry. So what we have to go? We have to do project design, and then we have to choose standalone system or off-grid system, right? The off-grid system standalone is maybe my previous one. What do I have actually exercise? No. Okay, so new. So I name project's name new project. Okay, no problem. Now I have to go for the site. Choose it. So I will choose it like IUB Dhaka Anisha. So data. Okay, so data. Okay, fine. So what it shows that please save the project. Fine, save. Right now it's actually giving the instruction. Orientation is not defined. So as far as we already learned about it, the 30 and 0 it will be fine. Yearly radiance shield is required. Fixed tilt. Okay, fine. Everything is done. Already learned about it. Now let's come to the point. Users niche section. Okay. So user niche section. Right now I need some help. Help from the slide because it's so tough to memorize all of this stuff. Okay, this one. This one is the load, right? Sorry. Yeah. Light is 4. Okay, 4 quantity, 25 watt, right? Let's go. Light need 4 quality lamp LED, and each one was 25 watt, right? So it would be specify hour. So I have to, it would be like for 3 hour. Okay, so it would be for 3 hour per day. Okay, so it's automatically calculated. The 300 watt hour daily energy is required. Then comes to the TV, PC, mobile. Let's come to TV. So here from manual calculation we choose in AC system, but as you can see, PVsyst it will consider DC. No AC system is in here, so you are not getting the AC system specification. So think of DC-DC system. So TV is 100 watt, 100, 102, 1 and 100, 102. Okay, then go to PVsyst 100. It was like 1 TV. It was like 100, right? And operate just very good. And then another one was desktop, which was also for 100, 101. Okay, fine. Desktop. So there remains no other options for desktop. So I am considering the domestic appliances will be desktop. No worries. You may rename it as far as I can know. You may rename it. So I don't want to specify some time. And it was like for 1 hour. Okay. So now you can see that it's already automatically calculated that how much amount of energy watt hour is required. Total daily energy is required is 60. 624. Monthly energy is 18.7 kilowatt hour per. Now it's actually specified. It's the warning sign that hourly distribution. Specify hours. Okay. So let's come to hourly distribution. So first of all, it shows that lamps. Okay. Lamps, it shows 3 hours per day. So now consider that when you will enlight your lamp, you will switch on your lamp. So let's say from 7 p.m. to 7 to 8, 9, 9. 7 it will be like 19. It shows 1 hour. 7 means 19. No? So this one. So 18 hour is in here, 19 is in here, 20. So for 3 hour total, our relative will enlighten. And it's actually showing you the graph automatically. So no worries to build a graph by using the Excel or any other software. It's not required. It's so nice. And then consumption rate TV is for 2 hours per day. Okay. So when we are want to entertain ourselves by daily number one or something, it's for 2 hours, right? So let's consider it from 20 to hours. So look, the pattern automatically change. And then domestic appliances, for that means our desktop, we'll use it for 1 hour. Let's choose one. Let's choose this value. Just roughly I'm choosing. Just only for 3 appliances, our graph, hourly graph. Okay. Or is okay, fine. And consumption definition by yearly, seasons, or months. So just for simple, we are choosing yearly. That means for the whole year, our load curve will be exactly the same. Just choose. If you want to specify that, you have to choose these options. Fine. So orientation done. User need done. Now it comes to the system. So we let's come first storage system. Storage means battery system. So here it's actually automatically calculated that accepted LOL percentage. LOL means, as you can see, the defined desired pre-sizing condition. It actually defines the losses value. Autonomy battery is 5%. Okay, fine. Keep it the same it is. Enter the requested autonomy. We have considered the autonomy. It will be like 2 days. Okay, as far as I can remember, the days. Fine. Now let's do the battery voltage. Okay, so if you can remember, the from the manual calculation, we actually choose the battery voltage. Operational voltage, it will be 24. So look, it's actually calculated. The suggested capacity for battery bank is required 61 ampere hour, and suggested PV power is required 184.9 watt power, which is nominal. Okay, so let's come to this section. So first, battery. So battery section. Okay, so I'm choosing not a specific companies. You may choose a lots of Tesla companies, Sony, Rolls, everything, Panasonic, PowerPeak, lots of batteries are over here. But we are choosing, let's say, all manufacturers to keep it simple. Technical. Okay, so let's consider it. Let's go through that. So, however, the main problem is 12 volt, but 50 ampere hour. Look, here there remains no option like 21 ampere hour. I am not getting that ampere hour. So 2 volt is there, but not 12. So 12 volt, we are getting 100, which are available in here, 151, 150 ampere. So let's choose 101 ampere hour because I have no other option. If I choose the Hoppiki model, so let's just choose. It also, showing the same exact result that two batteries in series is required. Of course, it will be because it's 12 volt. The operational voltage is 24, so two batteries are required. Series. So fine. Temperature mode, fixed temperature. We are actually considering fixed temperature 20 degrees Celsius. So keep it up. Please choose now the PV model. Let's PV array. Okay, so look here, for the standalone system, we require to require the value for plant power. However, in this case, that is the off-grid system, is not required it at all. It's already planned. Why? Because already I have specified that which kind of load or what is my demand pattern. Already give the no worries. However, you can again change it, but I would recommend not to do that. Okay, so let's come to the PV module section. Which PV module you want? Fine. So PV module section, just we as far as I can choose for 100-watt power for this. As far as I can, but please give me a chance to see. So as far as I can remember, the power output was like 100 watt. So let's choose 100-watt power. So for longy solar, as you can see here, it doesn't give us the option for 100-watt power peak, but you can choose any one of it. But to make simplicity and to make it same as I have shown, so I want to choose 100-watt power. So just any one. All manufacturing I'm choosing because I want 100-watt power solar module. Okay, then now choose 100-watt power. So if you choose 300-watt power, I would say that's better. But just to make it similar with the calculation, I am just choosing 300-watt power. That would be good. Why I am saying? So that means less number of solar panels required. Whenever you are choosing 100-watt power, that means a lots of amount of solar panels. There is a cost issue. You have to do that kind of analysis also. That, okay, 300-watt power, it gives me the less amount of cost, or 400-watt hour, it gives me the less amount of cost. And also space is also a big issue. Okay, so consider it in mind. So let's consider 100-watt power, and I am considering it like peak voltage, like consider like volt and silicon monocrystal sun, and the company name is sun. No worries. So it actually giving us the information that the maximum point voltage VMP 60, that means at 60 degrees Celsius to 64. So right now we have to consider about the controller. Okay, so controller position. So okay, so here a lots of controller system is in here. Master Volt, Morningstar, Nest, Pico Power, Nepal, Steka Solid, oh, lots of. So what I just choose Master Volt. Okay, no problem. And right now I have to choose a controlling system. So let's choose 12 to 24 volt system, 12 ampere. Okay, so that means maximum charging it can charge 12 ampere, and the discharging rate is 8 ampere. So just choose. Let's I'm choosing. Look, here there remains no notification. So no notification means it's absolutely fine. It will done perfectly. And the modules in series, it's actually showing it automatically. 2 module will be in series, 1 module will be in parallel connection. And as you can see, the operating condition, the maximum voltage, that means at 60 degrees Celsius, it would be like 32 volt. And whenever it's minus 10 degrees Celsius, which is really uncommon for our country. However, just choose it because, as far as I said, think global, because you are a global people, global citizen. So that time at minus 10 degrees Celsius, it would be like 51 volt. Okay. So I would say it's fine. It will work. Okay. Because there remains no notifications over in here, so I would say it is definitely workable. And the IMPP standard temperature condition testing standard temperature testing condition, it would be like 5.3 ampere. That means at 60 degrees Celsius, it's at 20 degrees Celsius, it would be 5.6 ampere, and also in minus of 5.6. Okay, so it shows that is known for 200 watt per. So each and everything I would say is fine because there remains no notifications over here. So Okay, now we are going to the last section. That means we are going to simulate. As far as I said, the optional is not required right now. So run simulation and showing, and then okay, we want to save. Okay, okay, fine, and then go to the report section. Very good. So we got the report. So we already stated that what kind of system it is. Standalone system. The tilt angle 30 degrees is about 0. And also the PV modules model number and the original datasheet name is in here. 2 modules is required. Parallel is 1 string. And unit nominal power. That means per module, per solar module, the nominal power is 100 watt per peak. So total it would be like 200. And yeah, the MPP, that means at maximum power point tracking, the voltage will be 34 volt current. And also one important thing, that module area, total area is also established and also predefined in here, that you need 1.3 meter square, okay, for total area it's required. And then loss factors is also, it's also written in here. Battery section is also, written, that which model you have choose to in series, and temperature coefficient, charging discharging rate is in here. So fine, let's go to the next page. Let's go into the next page. Okay, I have to go through the manual. So next page, in the page 2, it's actually showing you the hourly profile graph and showing it you that is spent by consumers 24 hours a day it will work. The total daily energy which is actually required 624 watt hour per day, and is also calculated simulation variant model, that is for a standalone system. The global users need, constant, it will be constant. As we have choose like for whole year, the whole year our demand will be the same, so it's actually okay. It shows that 228 kilowatt hour per year is required, it will consume. And then go to the third. Yeah, it's the nice, I just love it. Here as you can see, okay, look, the available energy 253 kilowatt hour per year. Okay, specific period is liquid, and excess unused amount of energy. Used amount of energy is 202.5 kilowatt hour per year, and excess unused energy is 24.9 kilowatt hour per year. So it's huge. It's not good, because 24.9 kilowatt hour per year we are actually is unused. And the reason is for the batteries actually. The performance ratio is like so low, I would say 51.8, not so good, not so bad, since it's little bit higher than 50%. So that means if we consider the standard temperature or all of these things are in the standard condition, if we consider if we make the ratio between this system and that system, then it will give us 51% efficiency rate. Okay, solar fraction is in here, time fraction is here. Missing energy, it shows 25.3 kilowatt hour per year. And let's zoom it. So here it shows that, okay, so rate actually indicates the applied the useful amount of energy, and the what I can say, the navy blue color is also so high, and as you can imagine that what is the loss. Look, the LC, the collection loss, that means the PV array loss is so huge amount of, okay, in this system. The unused energy is also in here, and the LS system losses and battery charging is 0.35 kilowatt per year. And the performance losses is also showing that if it is like the 100%. So okay, so let's say the standard simulation analysis will be in here. That means the production rate for the January month, it would be in like this 0.9 let's say kilowatt. However, my system, what we have designed, it would be like 0.45. Okay, so there remains a huge amount of gap. Okay, so we are not fulfilling this energy. Okay, so we are lacking. Fine. And then, yeah, we already showed it to you. And then the last, okay. And it's the loss profile. So here you can see the losses. So here we can state that, look, the huge amount of loss is actually for this one, minus 18.1%. Huge amount of loss. It lost to respect to the MPP running. That means for maximum power point tracking, it actually, it takes, it actually draws, it drains lots of energy. 18% of energy losses due to this system, and then 12.5% loss PV loss due to the temperature, and 9.8% loss due to the unused energy. That means full battery loss. 9.3 battery efficiency losses, and energy need of the whole user and supply. That means energy supplied to the user, it would be like 202.5 kilowatt hour per year. And what we will get, what actually our required, that was like 227.8 kilowatt hour per year. Okay, and the efficiency, as I have stated it before, the photovoltaic systems, the PV solar modules efficiency rate till right now is lower. It's so low. It's like it's almost, I would say, 20 to 30% till right now. So this chosen model is only 18.989. That means 19% efficient. Our PV solar modules efficiency is like 19%. So that's it. So is there remains some time so that I may deal with these issues, since it was like 51%. So maybe I will get some time, little bit, to make it like 80% or something, or it will be fine for you.
Sir, would it be possible to ask a few questions?
Yes, you can ask your few questions. Can you tell your name and
Yes, of
university, and
course.
you can continue your question?
Okay, of course. So my name is Jawad Hassan. I'm from the EEE Department of Independent University, Bangladesh. And my question was regarding the normalized energy, annual normalized energy graph that we saw a few minutes back, and also during the grid tie-in example. So we saw that a significant portion of the loss was due to collection loss. And now what I was wondering was, is this the collection loss that the one that's being referred in the graph? Is this the same as the loss due to the charge carriers in the cell itself not being absorbed by the bus bars or the contacts of the cell? So is that the same thing as the collection loss that's been mentioned here? That was my first question, and my second question was, in PVsyst, is there any way to import data about other organic solar panels or other organic cells? The example that was used was monocrystalline silicon. So I was wondering if there would be any way to perhaps import data about, let's say, organic solar cells, because as we know, currently organic solar cells are the next thing in the market because their energy conversion efficiencies are much, much higher and much, much better. So these are the two questions that I had. Thank you.
Okay, for second question, your question, what actually you said, mono organic or hybrid?
No. So just organic solar cells.
Organic solar cells. So what
So,
actually your question it was about?
so yeah, so I was wondering if there would be any way to import data about organic solar cells into PVsyst.
Okay,
Yes.
okay, very good question. Yeah, you can import as far as I know. However, as far as I know, it can be done, but you have to go for advanced section, or actually I didn't do it by myself. However, I'm really sorry, since I don't know. I actually not included any other specified, classified things in here, and then make it. But as far as I can understand, it can be done, because it's almost similar to the Proteus software. In Proteus software also we include lots of things like design modules in the C drive folder or something like that. However, this software, I guess you will get that kind of option, and you may contact it with the directly to the PVsyst companies because the mailing options are indicated. So no worries. But as far as I can uh, know, as far as I know, okay. So just go for the system. Let's check it out. Let's give me that kind of options or not. Just for ABB, it's okay. Or 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 you may actually go through this or you may actually search for each and everything, okay, each and every renowned companies, maybe for this particular specific organic cells, maybe there remains one company who actually deals with it. Let's say for Gigor, they may produce this kind of cells, so all solar cells it would be like this. So no worries if it is enlisted, so no worries. But if it is not enlisted, so that time, yeah, maybe you have to talk with the companies. So I guess they will help you. And your first question is about, could you
Thank
please?
you, sir. Yes, sir. My first question was about collection loss. So the one that's being, yes, referenced in the graph. So I was just wondering if this is the same collection loss as the one that we see for solar cells where
Of course, of course,
we
of
do
course,
charge carriers. Okay, okay,
of
okay.
course, of course, of course.
Thank you,
Collection
sir.
loss, that one. Okay, thank you. Yeah. Any other?
So there is another question
Yeah.
uh, from MD Faisal Ahmed. It is possible to simulate an autonomous solar system in PVsyst.
Autonomous means it's, I would say it's semi-autonomous. Okay. So if you go through all of this, procedure, so that time you can see you must have to give at first. You must have to give the orientation. So it is not autonomous. Okay. So we have to check it out. The yearly addition, you have to check that in which value it will be the perfect. Automatically, it will not give you the whole system design. It can be done because since it is actually dependent on the user load, user demand, so you can make it autonomous. Let's say for off-grid system, so my demand is, let's say the fan will be operating or will be in operating mode, let's say 3 hours, but for neighboring, for neighbor, that time maybe he required like 5 hours. So that time you can make a generalized system for each and everyone. So you have to deal with each person. So it's, you can say it on general that okay, uh, I guess it is not can be done. It's semi-autonomous but not fully autonomous.
Okay, sir. Thank you. Next question is from Joel Ahmed. He wrote, "What is the significance of this parameter called tilt?"
Field or tilt.
Uh,
Tilt.
Joel Ahmed, are you there?
I guess
Sir, so greetings, sir. My
yeah.
name is Jal Ahmed from Triple Department, American International University, Bangladesh.
Very good. Thank you. Thanks a lot for joining.
Sir, yes, sir. Sir, just to, sir, the tilt I'm talking about, that tilt 30-degree, because I've been seeing this. This is a synonym from the on-grid power solar power plant. So that's why, sir, I'm curious to know that is this parameter being used in this uh, in any other solar panels that we're seeing
In
these
any
days?
other?
I mean, solar power plant, that is.
You're questioning about tilt 30-degree, right?
Yes, yes, 30-degree. I mean, because I've been seeing that in solar power plant, they're using this parameter called tilt. So that's why I'm curious to know that how significant it is.
So I can say the tilt is basically an angle because it depends on when we set it to the ground or the upper area. It depends on basically which area we gonna put. The degree will, the angle degree will vary upon that area. So 20 to 30-degree means it's the most efficient way to collect the solar radiation from the sun and generates more power with consuming more heat. That I can say about it.
Yes, okay, I got it. Thank you,
You
Faraz,
got?
for the answer. Thank you very much for the answer.
Welcome.
So,
Meanwhile, thank you everyone. আজকে আমাদের অনেক টেকনিক্যাল ডিফিকাল্টিস ছিল and the sound was not proper. So যখন আমাদের ইউটিউবে আপলোড করা হবে তখন I guess properly you guys can hear and ওখান থেকে দেখে নিলে হেল্প হবে। Though অনেক টেকনিক্যাল ডিফিকাল্টিস এর পরেও আমাদের অনেক participants, at least 55 people were there with us throughout this workshop. So thank you so much for being with us এত কষ্ট করে। At the same time, we have our YouTube link in the comment box. So যারা যারা কিনা এখনো সাবস্ক্রাইব করেননি IEEE স্টুডেন্ট ব্রাঞ্চ, আপনারা কমেন্ট বক্স থেকে লিংকে গেলে আপনারা IEEE স্টুডেন্ট ব্রাঞ্চের ইউটিউব চ্যানেলটা পেয়ে যাবেন। সেখানে সাবস্ক্রাইব করার মাধ্যমে আপনারা 2-3 দিনের মধ্যে you will get the workshop video বা রেকর্ডিংটা ওখানে পেয়ে যাবেন।
So what I was trying to say that if you choose the tilt angle as 0, so that means your solar panel, it will be horizontal. It will be in the horizontal region. Okay, so that means there will be no angle between the ground and your solar panel. So that time, as you can see, the power which we are getting is lower. We are not getting the maximum amount of power. It is like 1 kilowatt hour, let's say. But whenever we are choosing like tilt angle like 29 degrees, that is for our country 29 or 30 degrees, so that time there it actually creates one angle with the ground. Okay, so that time we will get the maximum amount of power. So it doesn't mean that it is only specified for off-grid system or on-grid system or hybrid system. For each and every system you have to consider the tilt angle, and also you have to consider the azimuth angle. Okay.
Shaheen Parvez, if all
Yep.
the appliances run at the same time, then will the off-grid system continue?
Yeah, of course we are actually designing it by that way. Okay, so whenever we are designing off-grid system, okay, so that time we are actually considering that these systems will be working. Like if I go for this one is the okay, so it's the grid tie system. Okay, so if I go for off-grid system, so you can easily, whenever I actually showed it to you, first we make sure that which was actually our load user needs, and we actually applied it that okay, for lamps for 25 watt hour, and it will be for 3 hour per day. Okay, so we hourly distributed, and look here actually we are the same. Look, domestic appliances, so that means the computer, it was chosen in 19th hour, 20th hour. Here the TV, it also will be working position in 20th hour, and also the LED, it will also work in 20th hour. So that means we are already considered it that okay, at the same time all of the 3 things will work at the same time, so no worries about it.
Thank you, sir. There is
Yes,
next
sir,
question
thank
of
you.
Saiful Islam Leon. With this angle, I think it is 38-degree angle, we can get the maximum radiation from the sun.
Yeah, he's right.
He's
So
just giving his opinion, I guess.
yeah,
Uh,
but he is true. Yeah, he's right
okay.
that whenever you are choosing the 30 degree, because it's area specific, and we already choose it for IUB. So it doesn't mean let's say I am living in Puran Dhaka, okay, old Dhaka. So it doesn't mean that in old Dhaka specifically for my geographical location it would be 30. So maybe it would be like 35 or 26 or 23, but you first have to download the meteor data for your specific area, and then you have to calculate, you have to play with it, that at which angle you will get the maximum amount of solar radiation. Thank you.
Okay, so someone is Muhammad Ali Siddiq is asking, can we simulate dual axis solar panel in this software?
Dual axis solar panel.
Yes,
Yeah.
sir.
Yeah, you can do it, because I actually choose it like fixed orientation as far as I can remember. Yeah, orientation, look here, it is fixed tilt plane. Okay, you can see it. So here he said it like look here, there is lots of options like horizontal axis unlimited trackers, one axis tracking vertical axis, tracking sun shields, two axis tracking planes, tracking two axis. So there remains a lots of options in here. Tracking two axis frame, north south frame, north south direction and east west direction. So there remains a lots of options, but for simplicity, actually, we choose like okay, it would be like fixed tilt plane. Okay.
Okay, so MD Faisal Ahmed is asking how many solar panels generally we need to create off-grid system. Does it depend on our demand?
Of course, it depends on your demand, and also it depends on the power output of that solar panel. And as far as I said, let's say my power demand, which is required, is like say 300 watt. Okay, so now if I choose 100 watt solar panel, that means the solar panel which maximum output power will be 100. So that means I need three solar panel. But let's say if you choose 10 watt power solar panel, so that time we need 30 solar panels. So it depends.
Okay, so Faraz Al Islam, do you think we have any other question?
No, we don't have any other question. We can continue with you.
Okay. Yeah.
Faraz Al Islam, basically, I just want to know that do you have any other questions from your mind? So you may ask me, because you are reading all of this chat box, the questions of chat box. But do you have
Yes.
personal questions? And
No,
also, it will
sir.
be applicable for Anisha also. If you have any doubt in your mind, so you can ask.
No, sir. Right now, I don't have any question because you have clear cut everything. So when I'll do this work, if I have any question or if I face any problem, then I will ask you personally.
Actually,
Nothing real.
you know, since you are my student, I got you in my class, and in
Yes, sir.
which way I'll teach that each and every time I ask you the question. Let's say what will be this. I am asking the question. You are now in position to give me the answer. So for that reason, I am actually asking you if you have any doubts in your mind. Please ask me. I will try my best to give you the answer.
Sir, right now I don't have any doubt. If I have any doubt when I'm running this software or anything else, then I will contact you, inshallah.
Okay. Alhamdulillah. Thank you.
Okay, so Faraz Bhai, is Razak sir here?
Yes, yes.
Sir, sir.
Okay, so sir, we have a small token of appreciation for our
Yeah, sure, sure.
speaker. So Faraz Bhai, please present the certificate.
Okay.
Oh my God.
Oh, okay,
Yeah.
Anisha, I'm presenting
Okay.
So we have a big packet of kachi biryani.
online Kachibiyani, sir.
All right. Okay, that's good. So actually, I was present from the very beginning to until now. So you can see that this was a very wonderful experience, especially for the students who are new with PVsyst. And I think a lot of things they have already learned. But as I said, that this is just the beginning or the getting started. So students who joined today, so please just start from here. Okay, thank you very much, Saurav Dash. And okay, Faraz, let's present the
Okay, sir. Thank you, sir. I'm presenting
token.
now.
Oh my God.
Sir, here is your
I'm
certificate.
blessed. I'm blessed. It's so lucrative, beautiful, amazing. Thank you. Thank you. Thank you.
Welcome,
Thanks a
sir.
lot. But I'm missing the clappings actually.
Oh, okay.
So everyone turn on the yeah. Okay. So we are also glad, sir, you were amazing, and এর সাথে সাথে অন্যান্য অনেক স্টুডেন্ট ব্রাঞ্চ থেকে আজকে অ্যাকচুয়ালি অনেক সিগনিফিকেন্ট ছিল ব্যাপারটা। আমি বুয়েট স্টুডেন্ট ব্রাঞ্চ, AIUB, and then there was people from Dhaka University, even সত্য কি বুয়েট স্টুডেন্ট ব্রাঞ্চের চেয়ারও আজকে আমাদের সাথে ছিল। সো আই গেস সবাই অনেক বেশি শিখতে পেরেছে ফ্রম দিস ওয়ার্কশপ। অ্যান্ড বাকিটা তো বললামই, যেটা আমাদের একটু টেকনিক্যাল ডিফিকাল্টিস ছিল, ওটার জন্য আপনারা একটু ইউটিউবে চেক করে নেবেন। অ্যান্ড থ্যাংক ইউ সো মাচ স্যার ফর বিং হিয়ার উইথ আস। অ্যান্ড আমি সবাইকে এখন রিকোয়েস্ট করবো টু টার্ন অন দেয়ার ক্যামেরা। আমরা একটা স্ক্রিনশট নিয়ে নিব অফ আওয়ার টুডেজ ওয়ার্কশপ আর কি। সো যাদের যাদের প্রবলেম নেই, প্লিজ টার্ন অন ইউর ক্যামেরাস।
Sir,
I'm not
where
sure.
are you, sir?
I'm also searching. Where am I? Because saying I'm not. My
Sir, we
screen.
can see
Yes,
you. We
sir.
can see you.
Really?
Yes,
Yes,
sir.
sir.
Yeah, yeah, on the screen.
We can see you. So Faraz bhai, just take a screenshot.
Okay.
Yeah. Saurav, if you want to see you, then just click on the grid at the top right corner. There is a small picture of yourself. You can see.
And thank you so much again সবাইকে পার্টিসিপেট করার ইভেন্ট গুলোতে আপনারা এভাবে পাশে থাকবেন। এন্ড স্যার, রাজাক স্যার, এন্ড আমাদের ট্রেনার এন্ড আইএস সবাইকে থ্যাংক ইউ সো মাচ আজকে একটা ফ্রুটফুল ওয়ার্কশপের জন্য।
Thank you so much, sir. Ajak sir especially, and also Shoaib Sharia sir, and also Kafi sir. I'm really grateful for arranging this innovative session. Thank you. Thanks a lot.
থ্যাংক ইউ স্যার।
You can close the meeting. Yeah.
Okay, sir. Assalamualaikum everyone. Allah Hafiz.